Right. Again, good afternoon to you class. For today, for hydrogeology, we'll be talking about our second exercise. And we will be just discussing basically we'll just have a tutorial for this meeting. Right? Right, as you can see, we have various topics here: runoff, streamflow recharge, Darcy's law, groundwater storage, and flow nets. Okay, and the whole page is like 30 pages. Rule exercise is like 30 pages long. But of course, this also includes the concept. So it's not really, so it's quite voluminous because of the refresher refresher sections here, right? Now let's start with the watershed runoff. Okay. And of course, you can refer to the chapter 3 of CRESIC 2008 for the concepts. Okay. All right. Now, as I've discussed in the first exercise, we talked about the watershed or the hydrologic budget, which involves uh, which involves basically just looking at the watershed, okay, and just observing its boundaries. Basically, how much water is entering the watershed and how much water is exiting the watershed. Okay, so when we were talking about the budget, we were only concerned about the end, basically the boundaries and the quantities of water, okay, at the end of the processes. Now, there are certain cases, particularly for agricultural modeling or flood modeling, where you actually have to look at the sort of real time or uh, time varying quantities of runoff and recharge. Okay? I'm going to emphasize here that precipitation basically is the water that's entering your watershed, and it basically gets partitioned into your runoff and your recharge or the groundwater recharge. Okay. And this partitioning, of course, will depend on the basically on the capacity of the ground or the soil to hold water. Okay. Okay. So whatever is left after the ground has started storing water will be turned into runoff. Okay. So I guess you're already familiar with this chart. Okay. Okay. And also the SCS method. Okay. Okay. And I'm just gonna give you a refresher on this SCS curve number. So again, this is the SCS equation. Q or discharge is equal to precipitation minus negative 0.2 times S or the maximum retention. Okay. So water retention, this includes your infiltration, or water that's percolating into the soil, also the water intercepted by vegetation, and also evapotranspiration and storage in the surface depressions, or basically the puddles. Okay. And you can estimate this number or basically calculate this value by using the curve number. Okay. And you can see in this relationship that water retention in inches is inversely proportional to your curve number. Basically, the higher the curve number, which is maximum value is like around 100, the higher the number of the curve number, the less infiltration you get. Okay. And this is a table for estimating the curve numbers. First column is the cover type, basically the type of vegetation you have. Second column is your hydrologic condition, which is basically how much vegetation cover do you have in your soil. Less than 50% vegetation is considered poor. 50 to 75% vegetation is fair. And more than 75% vegetation is good. Okay? And you will notice, basically, the more vegetation you have, as by experience, usually it translates to more infiltration. And you can also observe here that good hydrologic condition also means lower SES curve numbers. And then the soil groups are A, B, C, D. These basically translate to A is your sand and gravel. B, I think it's your well-drained soils, usually loam soils, or basically soils that have equal parts of silt, sand, and clay. C is mostly your silt, and D is mostly clay. Okay. All right, for the tutorial, you have a creek, right? And you're basically interested in knowing how much runoff, okay, how much runoff will the creek get from its watershed given a precipitation. Okay, from runoff, it goes to precipitation. And your watershed has an area of 10 square kilometers. And 1/4 of the area is covered by bushes and sand soils, while the 3/4 or 75% is covered by woods and underlain by clay soils. Okay, so you have two types of cover, and we will call them Kalapatan A and Kalapatan B respectively. Now, so we start here with getting the curve numbers. For Kalapatan A, you have bushes and the soil is sand. Okay? Bushes or brush. This is around in this area. And then you have sand. So that's group A. Okay? Therefore, your value is just around 48 to 30. Okay? So the hydrologic condition was not given. So you can probably estimate the value is somewhere between 30 and 48, just to be safe. So that's 38 plus 48 divided by 2. You get like around 39 and 48. Or just for this exercise, you can just assume any hydrologic condition. Okay, so I'm gonna be lenient on the hydrologic condition that you use. Okay, in this case, we'll be using 48. Okay, and then for Kalapatan B, we have woods and then clays. So woods and then clays. Soil type D. So it's anywhere between 83 and 77. So let's assume we have a good hydrologic condition. So we get 77. Okay, so we have these values. Now, the next step is to just calculate the water retention. Okay. So this is basically the depth of water or depth of the precipitation that will be retained by the ground. Okay. So we just apply equation 3.4. Okay. So S is equal to 1,000 divided by Cn minus 10. Okay. So let's try that. So let's start with 48. 1,000 divided by 48 minus 10. And you get around 10.8 inches. Okay. So we have like 10.8 inches. Basically, that is the inherent capacity of your soil. No? That's basically its maximum capacity for water storage whenever you get some rain. Okay. Okay, so basically when you have a rain, this cover can intercept as much as 11 inches depth of rainfall. Kalapatan B, we have 77. So 1,000 divided by 77 minus 10, and that's around 3. Okay. So that's your value for Kalapatan B. Okay. So these basically are just the capacities for storage. And then for the actual runoff, basically the storage will try to take away some water from the precipitation, but it's not a straightforward arithmetic. Okay, so we have to consider other factors like the okay. So the storage will not be perfectly getting all the water. So we have this equation here, okay, and we can basically calculate that. So the first one is like 11, around 11. So what is our precipitation value? Our precipitation value is 100 inches. Okay. So we had 100 inches of rain. So that's actually a lot. That's like almost 1 meter of rainfall. And what we do here is let me clear this one. Q is equal to P minus 0.2 S squared. But I think this one's easier done by using spreadsheets. So let's try to have this one. Yeah, this one. This is hard. Okay, this is our formula. P is equal to, so precipitation is equal to 100 inches. Sorry. Copy keyboard. Sorry, I have a broken keyboard, so let's just do it through the calculator. So let's say you have 100 inches of precipitation. 100 minus your 0.2 multiplied by 11. Okay. So 97.8, you have to square that. 97.8 squared. Okay, so that is our numerator. Then for our denominator, we have 100 plus 0.8 times 11 That's 108.8. Okay. Sorry, it's not working. So okay, so that's what we're gonna get. We're gonna get around 87.9 inches of runoff. Okay. So that means you're getting around almost 88% conversion of precipitation water into runoff. Okay. Because we have so little precipitation um in your um in your bush area. Okay. Okay, so huh. Let me double check that value. So again, 100 sorry, 100 minus the quantity of 0.2 times 11 and square that value. You have 9,564. Okay, so that's correct. And then the other denominator is like 100. 100 plus quantity of 0.8 times 11, 808. Yeah, so we have a correction in the tutorial. The value here actually is so we have a value of divided by so we have like 87.92 inches of rainfall. Okay. And then for Kalapatan B, we have like okay, so for Kalapatan B, you have your precipitation is 100. Sorry, 100 minus 0.2 times 3, square that. And then the denominator is 100 plus zero point 0.8 times 3, 102. All right, and that will give you 9,880 divided by 102. You get 96.48. Okay. So you can basically just simplify this to two decimal places. All right. So basically, you're just getting more water from your wooded area. Okay. Wood with a clay soil cover. Okay. Now, the now we can just calculate now the total runoff, okay, in terms of volume. Okay, we just calculated the depth of the runoff, okay, per 100 millimeter rainfall. Now we can calculate the volume by multiplying that by the area of that sub-watershed. Okay, as you remembered earlier, so this is actually wrong because we only have 10,000 square kilometers. Okay, so this is 2 million. So 2.5 square kilometers is equal to 2,500,000 square meters, okay, and so on. So let's convert first the inches to meters. We actually have 2 meters here. Okay. So you have 2 meters of runoff. Then you basically just have to multiply it by the sub-watershed area. Okay, and then this one. All right. So we have now these quantities. All we have to do now is just multiply them and then add them together to get the total runoff for the whole watershed. Okay, so 2,500,000 multiplied by 2.232. You will get a value of 5,582,275 cubic meters. And then for this one, this is wrong. And then for Kalapatan B, we have a value of 2.4 meters times 7.5 million square meters. And that's gonna give you a value of 18,381,345 cubic meters of water. So now you just have to add them together to get the final value for the runoff. So this one, 18 million plus, sorry, 18 million plus 5.5 million, you will get 23 million, 23,963,620 cubic meters of runoff. Right, that is our final answer for this tutorial. Thank you for bearing with the corrections. Okay. Now for your problem in the exercise, you have another creek with a watershed with an area of 23 square kilometers. 27% is covered by grasslands underlain by clay, and then the rest is covered by woods also underlain by clays, and you have a precipitation of 100 inches. Right, so your problem is to calculate the curve numbers. So to simplify everything, assume the logic condition is is fair. Okay, so just assume fair hydrologic conditions since I didn't give it. And then also calculate the maximum water retention S, and also the runoff in inches and meters, and the volume of the runoff per for each sub watershed. So each sub watershed calculate their runoff, and also for the whole watershed calculate the total runoff. Okay? Pretty easy. And then the next exercise is about Manning's equation. Okay? This is a very important equation, especially in hydrology and hydrogeology. This equation is used to estimate the discharge or the flow rate of a river or an open channel, like a pipe or a canal, as long as you know the cross-sectional geometry of the channel or river or canal or pipe. And you also know uh, the rise over run slope of the channel, and also the Manning's equation, Manning's roughness coefficient, which will depend on the roughness of the channel surface. So you can see here, it varies from like a concrete pipe with a very smooth surface to like a floodplain with very dense trees. You have a very high roughness equation. Okay. Yeah, so this is really an important equation. You just need the geometry. You need the slope and the value of the Manning's coefficient. Okay. So this is a very simple equation. I'm not going to discuss how this is calculated, but I'm just going to show you some important definitions here. Okay. Basically, the channel geometry here that I'm talking about, the parameter that we need is what we call the hydraulic radius. Okay. If this is the channel or the stream cross section, if you're looking at the river through its cross section, you have the sides of the channel, the bottom. Basically, this dashed red line is what we call your wetted perimeter. Okay, this is the perimeter where the water is touching the channel. And then your cross-sectional area is basically this whole area or the whole cross-sectional area. And then the hydraulic radius is basically just your cross-sectional area divided by your wetted perimeter. Okay. All right, so that's your hydraulic radius, and that's the only important stuff you have to understand in this problem. And then for your problem, you have to do some calculations. You can just refer to this example for your tutorial. But this is very simple. I'm not going to discuss this one anymore. All right, let's skip to the groundwater recharge problem. This is quite tricky. We are gonna talk about the WTF, or the water table fluctuation method. Okay, this is not what the fuck method. It's water table fluctuation method. Okay. Okay, important concepts. One is the concept of a specific yield. Okay. Basically, if you have this, if you're gonna theoretically take a piece of soil containing water, so let's say this is a piece of your aquifer, and you just allow that piece of soil to drain out its own water by the influence of gravity. So of course, some water will drain out of this piece of soil, and that's what we call your specific yield. Okay? It's the water that will be readily yielded or be readily given up by the aquifer once you start pumping water out from it. Okay? Now, of course, there will be still some moisture left that will be left in that soil. Okay? Okay? Water, of course, tends to be clingy. Of course, it tends to cling due to capillary forces. And definitely, there will be still some moisture left in that soil. Okay? And that's what we call the specific retention. Okay? That's basically the water or moisture that is retained by the soil after you have drained out that soil or aquifer. Okay? So to be more correct, we call it an aquifer. Okay? So sometimes we're dealing with soil or fractured rock. Right? To give you a visualization, if this is your aquifer or this is your soil or your media, okay? Of course, your aquifer is saturated, it contains some water, and portions of it also contains your soil grains. Okay? We're gonna simplify it into a percentage, into a very simple division of volume. Okay? You have your water and then your soil. Okay? Then we can further split up this water into your moisture content or your specific retention or the water that tends to stay with the soil. And then you also have another portion, which is your specific yield or the amount of water that will be readily yielded or will be readily given up by the aquifer once you start draining it out. Okay? By the use of a pump or by the use of a gravity drainage. Okay, okay, so now you can also notice that these two elements, the specific yield and the specific retention, okay, there's some is your what you call your pore water. Okay. So together they form the water that's inside the pores of your aquifer. But once you start draining the aquifer, some of them will be yielded or will be given up by the aquifer, and some of them will stay in the pores. Right? Okay. Yeah, another importance of your specific yield. Okay. In terms of recharge, specific yield will dictate how much water per volume of aquifer can be drained out or recharged back to an aquifer. Okay. So if you have a high specific yield, what does it imply? Okay. It implies that you have more water available for extraction if you're doing some water wells or if you're doing some aquifer rehabilitation, you have a lot more water that can be stored in the aquifer. In terms of water level rise, okay, when you have a high specific yield, okay, the tendency is that you get less changes in the water table height. Okay, because you only need to lower, you're only draining out or per unit volume of the aquifer, you are basically getting a lot of water in an aquifer with a high specific yield. Okay. So you're basically the practical application of that is when you have an aquifer with a high specific yield, basically you have a lot of water stored in your aquifer. And once you start extracting water from it, since it has a lot of water stored in it, you only need to lower the water table by a little bit once for you to able to get some water. Conversely, when you have an aquifer with a very low specific yield, it means that you have to squeeze out a lot of volume of aquifer before you start getting some water. The easier analogy here is compare a ganda comparison. Compare, for example, a sponge or a microfiber towel versus a normal towel. So for example, you have a microfiber towel. Okay? So it only takes a little effort and fewer microfiber towels to get some water, no? Compared to a normal towel, no? Konti lang yung pipigayin mo. Okay? Basically, okay, so your microfiber towel is like your aquifer with a high specific yield. Okay. Okay, yeah, let's go to the tutorial. So if you have questions, just message or email me. Now for the tutorial, your water table fluctuation method is basically you're looking at this concept of specific yield, no? So yung concept niyan is pag tumataas yung water table mo, ibig sabihin nagkakaroon siya ng recharge. Okay? And ang alam mo lang actually is yung height ng water, yung rise or yung actual rise ng water table in units of meters, for example. So alam mo yung meters na rise ng water table, no, over time. Pero since you're interested in the actual volume of recharge of groundwater, you can use the concept of specific yield to convert that height change in groundwater table into a volume. Okay? So basically, iba-iba kasi yung response no, ng aquifers depende sa specific yield. So kapag yung aquifer mo mataas yung specific yield, hindi siya masyadong nagfa-fluctuate, no? Kasi marami siyang tubig, no? Kahit kumuha ka ng maraming tubig sa kanya, since marami siyang laman na tubig, hindi siya masyadong magfa-fluctuate per volume. But if you're dealing with an aquifer with low specific yield, sobrang konti ng tubig niya na ang dami mo nang binaba sa water table, konti pa rin yung tubig na nakukuha mo. So sobrang nagfa-fluctuate siya. Okay? Mas nagfa-fluctuate si aquifer with low specific yields. Okay, so I hope that I hope you understand that concept. Okay, so again, disclaimers, you can only use the WTF method for unconfined aquifers. You cannot use it for confined aquifers. Okay, mainly because for confined aquifers, ang nangyayari sa confined aquifers is it's like a diaphragm, no? Para siyang water balloon yung confined aquifers. Parang may pinipisa ka na lobo, no? And medyo complicated yung water table rise and fall niya, no? Compared to unconfined aquifers. Also, bawal din sa karst terrain because karst terrains have a lot of conduits, maraming daanin ng groundwater. Sobrang hirap ma-estimate or ma-calculate yung hydrologic properties ng isang karst aquifer. Okay? So step 2 is plot the water table levels per time. So the setup here is you have an aquifer. You have an aquifer. You know the extent of that aquifer, meaning in terms of area, coordinates. You know the extent of the aquifer. No, usually do some geophysics and some fieldwork mapping to delineate the extent of that aquifer. And then after that, you start drilling some observation wells on that aquifer. And then you measure the water table levels per time. Okay, yeah, ideal resolution is like once a week or less para captured mo yung fluctuations sa water table. So connect the troughs of the plot. Okay, so basically nagfa-fluctuate kasi yung water level, 'di ba? So high, low, or yung trough. So ko-connect lang natin yung mga lows nila. Yung lows na yun yung parang water table level dapat kung walang nangyaring recharge sa aquifer. Parang yun yung normal levels niya. Okay? Without the recharge. Measure. Okay? Then from there you can measure the recharge, no? By measuring the heights of the water table rise relative to that baseline. Okay. And then your multiply the water table rise by the specific yield to obtain the recharge. Then to obtain the recharge for a period of time, sum the error of the water table levels and then multiply it by the specific yield. Okay, easier. It's much more simpler to just talk about the example. So let's say we have your Kalapatan watershed. It's a shank aquifer that is also a watershed. No? Watershed aquifer, isa lang sila. Area of the watershed and the aquifer is 10 square kilometers. And then from pumping test, determine na yung specific yield niya is 0.08. Okay, so we have this date, and then your groundwater table levels in meters. Okay, so we also have precipitation, but for now you can ignore this part. Let's just focus on this data. Okay, so we have plotted the data. This is groundwater level in meters. This one, your x-axis is your dates. Okay. So you have a simple series of your groundwater table levels. Okay. And this is the peak and this is the trough, no? Ito yung mga trough natin. So next step is just draw a line connecting the troughs. Okay. And this purple line is basically the imaginary baseline, no? This is supposedly the normal groundwater level, no? Na nagpa-fluctuate through time kung walang nangyayaring recharge. Okay? Parang ito yung long-term na groundwater levels dapat. And then, to measure the recharge on a given day, you can basically just look at the spike, no? So let's say gusto mo malaman yung recharge ng March 4, you can just measure this height difference between the baseline water table and the groundwater level during that day. So this is like 40 meters, no? 40 meters rise. Okay. So 40 meters, just multiply it by the specific yield, you will get like 3.2 meters na depth ng water table, ng water rise, no? So just multiply 3.2 meters by the aquifer area, yun na yung total volume ng recharge for that day. Okay. Okay. All right. Now, if you want to measure the recharge for like a period of days, no, you just have to like huh, March 4. This is March. Okay, so this is the recharge for just 1 day. Okay. Just multiply the recharge by the area of the watershed. So 3.2 meters na recharge, and then multiplied by 10 square kilometers, you get like 3.2 million cubic meters na recharge ng araw na yan. Okay? If you want to do it for the whole time here, you can just estimate no the what fluctuation levels no per day or per week no. Pero since we just have a weekly data, you can basically just imagine, you can just paano ba? Let me annotate this one. Since medyo limited yung data natin, you can just imagine or represent these by like bars, no? Parang bins na sila. Okay, parang isa-subdivide mo na lang sila into 7-day windows. Okay? Okay, so parang ganyan siya. So itong week na to, so let's say itong first week, no? Itong first week, halos wala ka namang recharge. And then yung week ng February, yung week na nakasenter sa February 12, meron kang 7 days and meron kang fluctuation na 10 meters, 5 meters, no? So 5 meters fluctuation to. Ito naman ay, alam mo to? Sa week na centered on February 19, meron kang fluctuation na 15, approximately 15 meters. And then sa week na centered sa February 26, meron kang fluctuation na 45 to, let's say 15 to 45, that's around 30 meters. And then sa week na centered sa March 4, you have 40 meters fluctuation. And then sa week na centered sa March 11, you have like 45, let's see, 20, 45, that's around, let's say 25 meters. And then sa week centered sa March 18, you have like 5 meters siguro. And then finally, sa week centered sa March 25, you had like, let's say 2.5 meters. Okay? So all you have to do now is just each bar here, multiply it by your SY. Okay, so delta H or your fluctuation groundwater fluctuation multiplied by SY, and then multiply by 7 days and just sum it all, no? Just do the summation for this whole period. Uh, i- so pwede mong i-calculate yan per period, no? So let's say 5 meters multiplied by SY and then multiplied by 7 days, yun na yung recharge. And then, multiply mo pa siya by the area of the watershed. Yun na yung recharge volume per sa week na yun. Okay? So gagawin mo yun sa lahat ng bar dito to get the total recharge for that period. Pero since parehas lang naman yung SY nila, parehas din ng 7 days yan, parehas din yung area nila, pwede mo na lang i-sum na lang tong lahat ng fluctuation na to and you will get the total recharge for that whole month. Okay, so 5 plus 15 plus 30 plus 40 plus 25 plus 5 plus 25. You have a total of 145 fluctuation meters worth of fluctuation, no? And then just multiply it by your SY 0.08. You get 11.6 times your 7 days each times your 10 million square meter watershed. Okay. So you will get 800 million cubic meters of recharge for that period. Okay. Okay, so parang ganyan lang siya, no? I-divide mo lang sila into bins. Okay, so yung exercise nyo is just fill up this table, get the delta H per day, per date, then get the recharge, no? So delta H times SY, yun yung recharge mo. And then multiply it by the watershed area, and then you can get the volume of recharge per week. Okay, very simple. And then Darcy's law. Next topic is Darcy's law. Darcy's law. So basically what we're doing here is, I'm not sure kung na-discuss, I think na-discuss ko na doon ng isang lecture. Okay. So you should be familiar with that by now. And we have an exercise here. Basically, we have a permeability testing, no? Okay. I'm just gonna skip this part, no? Medyo simple lang naman siya. And then, confined and unconfined aquifers. Basically, this is just a research problem. You just have to research your aquifers, no? Different examples of aquifers. And then specific retention and specific yield. Okay. Okay. So gagawin mo lang dito is you're just gonna estimate, no, kung gaano kalaki yung ibababa ng water table mo when you start pumping out water, no, given the concept of specific yield. Okay. So just refer to the given example for your reference. And then finally, we have a problem in flow nets and flow boundaries. So ginagawa lang natin sa flow net is para siyang, basically parang nagko-contour ka lang din ng elevation, no? You're just contouring the like you're just like contouring elevations, pero instead you're just contouring the uh equipotentials or parang yung basically yung supposedly elevation ng water table. So if you're doing a flow net on an unconfined aquifer, basically kinokontour mo lang yung elevation ng water tables. If you're dealing with confined aquifers, ang kinokontour mo is yung uh, piezometric levels. Okay, so from there, once you do some flow net contouring, no, you can basically just estimate no yung hydraulic gradients sa isang area. Okay. And from there, you can basically estimate no the discharge of an aquifer at a given cross section. Okay. So there's a tutorial here, sundan nyo na lang yung tutorial. Okay. Okay, so may valid yan, no? Dapat yung may mga rules yan, no? So dapat yung circles touching all four sides, no? So basically each net, no, dapat may magkasyang isang circle. And dapat lahat ng tangents ng circle nagkakadikit-dikit. Hi Janelle, sorry medyo nag-start na ako kanina, no? So medyo patapos na yung lecture. Pero naka-record naman to, no? Don't worry.
Hello, sir.
Okay, thank you. Si Dan.
Sorry, sir. Hindi ko po agad nakita yung link po. Naghihintay po ako ng link, sir.
Ay, shucks, sorry. Nag-message ako sa
Pero
BB.
okay lang, sir. Naka-record naman daw po. Sabi po ni Dan.
Sorry. Nag-post ako sa BB message, pero
Okay lang, sir. No worries po.
okay. Okay, si Dan, wala pa. Na-traffic yata. Nakawa naman si Dan. So anyway, talaga buhay. So yun yung flow net. So basically, just follow the tutorials here kung paano magbuo ng isang flow net. And then after that, pag nagawa nyo na yung flow net ninyo, may isosolve kang problem dito sa... Okay, so meron kang dalawang reservoir dito and connected sila by an aquifer. So yung... So, itong Pegasus Lake, mas mataas siya, no? 120 meters yung elevation niya, and then meron kang Mariposa Reservoir, 70 meters. So yung tubig mula Pegasus, papuntang Mariposa, bumababa siya, no? And from there, all you have to do is just draw a flow net in this aquifer. Yung flow net nyo, just divide this aquifer into 4 columns. Okay, then basically just draw a flow net, no? Pero you have to follow the rules, no? Hindi pwedeng bara-bara yung flow net. Just draw a flow net here, and then from there, you have to basically obtain the discharge, no, flowing through this aquifer. Okay. So again, to calculate the discharge of an aquifer, you can use the Darcy's law. So Darcy's law is Q, or discharge is KIA. K is your hydraulic conductivity. Which is given, no? Given na siya dito sa problem nyo. Okay. I is your hydraulic gradient. So malalaman mo yung hydraulic gradient from the flow net. Okay. Basically, ano mo siya gagawin? Okay, so basically parang pag nag-construct mo na yung flow net mo, magkakaroon ka dito ng parang flow net lines or parang contour lines. Just like sa topographic map, no? And then from there, you can just, for example, just kung meron kang dalawang equipotential lines dito. So let's say, nabanggit na ng 70 tsaka 1. So let's say dito, so let's say ito yung isang equipotential line or isang parang contour line mo. Ah, shit. Clear muna natin. Okay, so let's say this is one equipotential line or contour line of your water table, and this is another one. So parang sa topo map lang siya, no? So let's say the value of this line is 100 meters groundwater table elevation in meters. So yung pangit na sulat ko. And let's say this one is like 90 meters naman. Okay. So again, yung pagkuha ng gradient dyan is basically just parang sa topo map, no? Just draw a line. And then, alam mo yung elevation drop dyan is just the difference between 100 and the 90. So basically the delta H here is like 100 minus 90 meters which is equal to 10 meters. And then yung path length mo, or let's say delta L, is just the map distance. So meron ka namang scale bar dito. So this is like 1,000 meters. So ano kaya yan? So let's say, I think this distance is around 1/3 of 1,000. So let's say your delta L is like around 300 meters. Okay. So hydraulic gradient, basically rise divided by run, or delta H divided by path length. 10 meters divided by 300, you get 0.033 hydraulic gradient, dimensionless. Okay? So, ganun lang yung pagkuha ng hydraulic gradient. Once you have constructed your flow net. Okay, once you've gotten that hydraulic gradient, given na rin naman yung cross-sectional area actually ng aquifer. Okay? Given naman yung thickness ng aquifer, tapos basically yung lapad ng aquifer, pwede mo naman ma-estimate dito sa mapa. Okay? So, it's like around 1,000 meters yung lapad niya. Okay? So, you have your depth of your aquifer or the thickness. You also have your width of your aquifer, which is approximately 1,000. So, may estimate mo na yung cross-sectional area ng aquifer. So, alam mo na yung hydraulic conductivity. Alam mo na rin yung hydraulic gradient, no? Once you've drawn the flow net. And alam mo na rin basically yung cross-sectional area ng aquifer given the aquifer thickness and the width of the aquifer. And from there, you can get the discharge. Alright, so yun lang yung buong exercise. Okay, sorry sa inconvenience, no, sa communication ko sa link. Pero, yeah, sorry yun lang inabutan yung lecture. Okay.
Sir, question po.
Sorry, ano yun? Ano yun?
Sir? Sir?
Oh, yes, yes, yes. Ano yun?
Um, regarding lang po dun sa link, sir, hindi niyo po ata na-attach po yung exercise? Or
Hindi ko
today niyo po
na.
ibibigay?
Sige,
Opo.
i-attach ko na lang din. Wait, then. Sorry, tapos yung lecture. Sorry, sorry. Ah, may ganun ba? Ganun ka pa sa bahay? Okay, yun lang. Ikakatapos na yung lecture. Pero may recording naman ako. Sorry ah. Hirap ng buhay. Ah, ano din? Tapos na yung lecture. So, basically, upload ko na lang din yung recording ng lecture. Tsaka yung exercise document. May galang ba? Galing ka pang Cavite, no? Sige. Ano oras ka ba umalis? Last test. Shit. Gamit na. Peters. Ako sa Paranaque ako eh. Siguro pag nag-commute ako, baka, mga 2 hours. Pero, yun nga, mahirap mag-commute. Wala akong kotse, so nagmamotor lang ako. Which is buwis buhay naman. Ano yun? May klase ka ba bukas? Opo. Paano ba yung commute mo? Nagbabas ka? EDEX. LRT. May nga na. Okay. Dahil na lang. So, upload ko na lang yung exercise document. Isa lang pala yung klase mo pag Friday. So, anong week na ba tayo? Week, week 6 na, no? Sige. Next time, pwedeng mag-text ka na lang din ng maaga para kung pares kayo hindi makapunta, i-online ko na lang para hindi na kayo mahirap. Okay ka lang? Hindi ka malungkot. Okay ka lang ba? Okay talaga ba? May bakit ka naman? So, tuwing kailan ka ba pupunta sa campus? I mean, anong araw ba yung may klase ka? Online na lahat? Ako lang ba yung nag-face-to-face? Putek. Ganun ba? Pwede pala yun. Okay, sorry sinusundan ko lang kasi yung grabe. Hindi talaga fair. So, wait lang. So, sige, Janelle, i-stop ko na tong lecture muna para
Okay,
mag-record.
sir. Thank you, sir.
Thank
Ingat po
you.
kayo.
And then, ano ba to?